All right, welcome to geometric sequences, which there will be some similarities between the arithmetic sequences that we already kind of learned about and the geometric sequences, but there will also be some differences. So I will start by telling you the definition of a geometric sequence. Again, the key for geometric sequences is that each term is obtained from the previous one by multiplying by the same non-zero constant. So the arithmetic sequences, you added the same value to get the next term. Geometric sequences, you multiply to get the next term. So in geometry, you probably dealt with similar triangles, and that would be what the blue triangles represent. If you have a triangle with sides 2, 4, and 3, and you happen to have a multiplier of 3, then this side maybe is would be 6. This side would be 12, and this side down here would be 9, and they are similar because they have a common factor of 3. So the algebraic definition for a geometric sequence is, and this is some notation that may be new, it is IB notation. It is what they use in the IB formula packet. So again, this is set notation over here. If we were to look, this is set notation saying the set of values is geometric if and only if, again, this double arrow both ways means if and only if, the division of or ratio of consecutive terms, so the one that comes after, and this is the one that would be before, equals r, meaning for every single pair of terms in the sequence, if you were to divide them, the latter one over the former one, you would get the exact same value r, which we call the common ratio. Again, similar to arithmetic because you had a common difference. Now we have a common ratio. And so for, again, the example 3, 6, 12, 24, 28, this is referring to like so if I were to look at these terms, the 6 would be the term that came a little bit later, and I'd have to divide that by the term that came before it, which is 3, and voila, that equals 2, and that would be what my common ratio was. And if I wanted to look at any pair of consecutive terms, so I could look at these two, in this red circle case, this would be 12, and that, because that comes later, divided by the one that comes before it, which is 6, that also equals 2. And I could do this with any pair of consecutive terms. I'm not going to do it with every one of them, but if I pick this pair of consecutive terms, the 48 would match with the second term in that pair, and divide that by 24, that's what this one would be, and that would equal 2. So my common ratio is 2 for every single pair of consecutive terms. And this n plus 1 just means the term that comes after this one. So if this is 6, then the term that comes after it is 12. So hope that clears that up a little bit. The geometric mean, which you learned about in geometry, is when you were to take these three values, and if they're consecutive terms of a geometric sequence, the geometric mean, which is this one right here, which we're going to call in the middle, would happen if I were to go A compared to B, and that would have to equal, notice that B compared to C. This is what you learned in geometry at some point, maybe. And then if I were to cross multiply, that's how we solve a proportion like this, two ratios that are equal. I would get B squared equals AC. And then if I wanted to solve for B, I would have to take square roots. So B would be the square root of AC. Now, if I do this in terms of looking at this as a geometric sequence, what we just talked about, and I look at these two terms, then I would have to say, instead of writing it the way I did in green here, B would be on the top because that comes after, that's the second term, A is the first term, so it would have to be B over A. And if this is a geometric sequence, then I know that has to equal, and I'm just going to change colors because I can. Now if I look at these two consecutive terms, C is the one that comes after B, so that would have to be on the top. and it would have to be in ratio divided by b. But notice if I do a cross multiplication on this proportion as well, I still get b squared as one of my cross products equals AC. And if I were to solve that, it would still give me this value. So this is the geometric mean as opposed to the arithmetic mean, which is what most people are used to. The arithmetic mean, we usually just call the mean, the average. You add things up and divide by how many there are. In this case, we multiply and then take a square root, because square root undoes the squaring, and multiplying, squaring is just repeated multiplication. So that's where multiplying is repeated addition, and when you divide, you undo multiplication. So that's the difference between the arithmetic and the geometric means. So that is tied into the idea of the geometric sequence as well. So now we're going to find a general formula that we can use for all geometric sequences. So again, we're going to start with the first term, and that would be u1. The common ratio is r, so this is my first term. It's kind of like with arithmetic. The second term would be u sub 2, the third term would be u sub 3, etc. If that's the case, and we've got a little example down here in the corner that we'll plug these numbers into in a minute, but what that's saying is that this is my first term, this is my second term, this is my third term, this is my fourth term, fifth term, etc. And over here would be wherever I am, my nth term. So if this is true, again, I'm going to do a little manipulation of values. If I were to use the formula we already talked about, that's saying that the second term divided by the first term is my common ratio. And notice that if that's the case, if I were to multiply the u1 away from both sides, I would get my second term, which is u1 times r, which is what this is saying. And if I keep going with that idea, the third term would be the first term times the ratio squared. And again, if you're not sure about that, if we look at our example, my ratio on this is 10 divided by 2, which is 5. And so the second term, if we use our formula, is the first term times r, so that would be 2 times my ratio of 5, that's 10. If I want to look at my third term, based on the way we're developing this, that would be the first term, which is a very important one, so I'm going to mark that, 2 times the ratio squared. My ratio is 5, so 5 squared. Order of operations, I have to do that first. 25 times 2 is 50. Check, that worked as well. And the reason that works again is u3 divided by u2 has to equal r, correct? Any consecutive terms have to be the common ratio. So if I multiply this u2 over here, that's great, but I already have a value for u2. It's u1 times r, so I can substitute that in place of this u2. So my u3 would equal the r times u1r, and r times r is r squared, and that's how we get to this formula for u3. So if we just keep going with this idea, notice that first off, notice that this is in each one. If I keep doing this, u1 is always going to end up in there. And notice that the ratio also ends up in there, but its power keeps going up by 1. But the power of this is always linked to the term in question. So if I want the second term, the power of my ratio is only 1. If I want the third term, the power of my common ratio is 2. Fourth term, the power is 3. So if we notice that trend, we get to the important formula in general for any geometric sequence. Any term in the sequence can be found by taking the first term times the common ratio raised to the power that is 1 less than the term you're interested in. So this is the big formula that we're going to use, and we are going to, that is in your formula sheet, so you don't have to memorize it. It's there, it's available. We're going to use it coming up right now. So I'm going to use that general formula. I've got a sequence, 8421.5 dot dot dot. I'm going to show it as geometric first, then I'm going to find the general term. So this is just finding the formula. The second part here is just asking me for the formula. So this just means I need to know the first term, I need to know the ratio, and then I'm going to leave this up there because that's the general term. In general, it'll have an n-1. And then I can find the 12th term by plugging in 12 for n. So first, show that it's geometric. To do that, I have to show that every pair of consecutive ratios is equal. So 4 comes after 8. Then I have to look at 2 and 4. 2 comes after 4. And this equals a half. This equals a half. And then I've got to look at these two. I'm making a bunch of lovely circles up here. Now that actually is just 1 over 2. So far, 1, 2, 3 work. And then this is 0.5 over 1, and 0.5 over 1 is the same as a half over 1, which is the same as a half check. And that's how I show it's geometric. I just show that the common ratio is the same, and I've done that. Now I'm going to find the general term. Now remember, I already know the common ratio is a half, and only other thing I need for this, here's the formula. I need to know the first term and the common ratio. That's it. So there's my common ratio. And I just need the first term. That's the sequence I gave you. So the first term is 8. So I can write this very quickly now. 8 goes in for the first term. I'm going to put the 1/2 in parentheses only because it's a fraction. And that gets raised to the n-1. Boom. That's it. That's all I have to do. And that is the answer to B. That is the general term of the equation. You don't have to do anything else. That's what it wants when it wants the general term or the formula to find any given term. And now to find the actual 12th term, I'm going to go back to my formula that I just did, is 8, and it was 1/2 to the n-1. Notice they're asking it for a fraction. So good news. Fantastic. So if I want the 12th term, it's really saying, what is the 12th term? That's my question. And that's going to equal 8 1/2 to the 12 minus 1. But I know that 12 minus 1, I don't even need to write that because I already know that is 11. So whatever, this is n-1, so if n is 12, I'm going to do some mental math. Now, I don't know what 1/2 to the 11th is, but I want it as a fraction, so what I'm going to do is, that means that this exponent gets applied to both the numerator and denominator. So I do know what 1 to the 11th is. I don't know off the top of my head what 2 to the 11th is. So I'm going to have to figure that out. But this is just 1. And now I'm going to do a little cheat. Oops, that's not what I wanted. That is something else. I wanted this. Boom. 2 to the 11th is my handy dandy calculator. 2 to the 11th power is equal to 2048. Fantastic game. If you've never played it, you should. It's great. All right, so that means I have 8, 1 over 2048. And now does 8 go into this? Because really what I have here, because this is 8 over 1, I have 8 over 2048. I'm pretty sure 4 goes into both of these. I'm just going to check real quick and see if 8 goes into both of these. And so I'm going to divide that answer by 8 just to do a quick check. And this divided by 8 is 256, which means my final answer will be 1 over 256. That would be the 12th term if I kept going in this. That's the first, second, third, fourth, fifth. You can see that I went from integers to a fraction, and those fractions are going to keep getting smaller. All right, you are going to try this one, all 3 things again. So go ahead and try all 3. Pause the video right now. Try all 3, and then I'll show you the answers. And then I'm going to have to stop this and create a second video because I know that you love these videos. So pause, work it out, and then unpause and check. So pause. All right, I'm assuming you have checked it. There's your first term is 5. Your ratio is 2. There is a formula for the 5th term, and the 15th term would be 8192. So when we come back with video 2, we're going to start on example 2.